Example 6. This one's a little bit more challenging than the last one, example 5. We're looking at the thermal conduction of two bars that are in series. If you think of it, it's kind of like resistors in series in ways. Remember, or we will study, I guess, later on. Resistor 1, resistor 2, and it has current that flows through it, I1 and I2. So when we study circuits, you're going to see kind of very similar ideas in here. All right? Except we're looking at pipes, right? And that are conducting heat. And we have a heat flow that flows through here, Q, steel over time. And then you have, again, a heat flow, Q, copper over time, right? And so the big idea here is that when you have conductors that are one after another, what we call in series, right? This is point number 2 in here, like this picture. The key idea to remember is that when you have two materials that are in succession with each other, then the heat flow through each layer is the same, right? So essentially Q1 over T and Q over T for the layer 2 are identical. They're in series. And there's some intermediate temperature in between here, and that's what we're trying to find actually. So let's get to the problem now. All right, so the first thing we're going to do, and we'll just erase this bit here, is we're going to be looking for that temperature T. Okay, so we can write down some of the given information. It's all in the picture, but yeah, well, why don't we write down the given? The given here is for steel, we'll just write T hot, I guess 100 Celsius. The length that it travels through is 10 centimeters. And the thermal conductivity for steel is given as 14 joules over seconds times meters times degrees Celsius. Then we have the cold temperature on the other side for copper. On the other side of it is 0 Celsius. We have its length is twice as long, 20 centimeters, and its thermal conductivity is a lot bigger, 390 joules over seconds times meter times degrees Celsius. What we don't know, I guess, so we also know the area. I guess it's a square. Right? You have to kind of think of it as like a square in here, right? This is a square in here. And so the area is, well, 2 centimeters by 2 centimeters. Or you could say 0.02 meters squared. So our area is 0.0004 meters squared. These are zeros, by the way. Okay, next. We're trying to find two things. We're trying to find the temperature in between the two pipes, okay? And then we also want to find the heat flow rate that goes through, okay? So let's start off, okay? So we're going to use the idea that when you're in series, right, we know that the heat flow rate through 1, so this is the steel, is exactly equal to the heat flow rate that goes through the copper. Okay? I think like you're in a race and you can't go any faster than the person in front of you if you're like tied together. You're all together going at the same pace. Okay, so now we now apply the thermal conductivity formulas. So we're going to put K for steel, area, then delta T for steel, all over L for steel, K for copper, A, delta T for copper, and L for copper. And I just left these as A because actually both of them are the same cross-section area. In fact, you could probably just cancel this out. Don't need the areas. They're going to cancel out. All right, at least at this part we don't need it. And we're going to be solving. Now K steel is given as 14. Delta T for steel, it's the higher temperature minus the lower temperature. Remember, it's going from 100 to here. So higher minus the lower is going to be 100 minus the unknown temperature of T. So 100 minus T. And its length is 10 centimeters. You can leave it in centimeters if you want, because it's just going to be centimeters on the right side and centimeters on the left side. Left and right have the same units. So then the thermal conductivity copper is 390. then the change in temperature now is going from the hotter temperature is now T, and the colder temperature is 0. All over this distance of 20 centimeters, or you can put meters if you'd like. Okay, so we can do some kind of cancellations, right? This becomes 2, right? 10 goes into 20 twice, and then basically rewrite this as, I think, 28 times 100 minus T equals 390T. All right, and then 2800 minus 28T equals 390T. And then we get T, how many T's do we have? We have 418 T's equals 2800. So this gives us a temperature of 6.7 degrees Celsius. Okay, now to find the heat flow rate through either one, because they're the equal, you just plug it in, now that you know what T is, into either the left side or the right side of this equation. So I'll just do it for steel. So it's on the left side, and we're just going to use K steel aluminum, delta T steel, all over L for steel. And so we have 14 times 100 minus the temperature is 6.7. Oh, I forgot the area. Let me move that over here. I need the area as well. What's the area? The area is, I need more space. 0.0003004, I think. That was what I wrote above, I think. Yeah. And then divided by the length, which is in centimeters. Now, probably would have been smart for me to put things in the correct units. So this should be in meters now. 0.1. All right. If I had more space, I would put units in here. But this is, if you remember, the thermal conductivity is in joules, seconds, meters, degrees Celsius. So this needs to be in meters squared for area, right? This needs to be in Celsius, which it is already, and this needs to be in meters. So when you plug all that in, I believe you'll get 5.22 joules per second. Okay. That's it. But I should just point out one little side comment on this. Suppose that I gave you the same question and I didn't ask you for this intermediate temperature in here. And you're just asked to find out how much heat flow is flowing through both of these bars together. And you might be, well, then I have to find the intermediate temperature. It's really long, right? If you don't want to solve for the intermediate temperature, there is kind of a shortcut way to solve for this answer here, to find essentially the total heat flow rate for series. So we use something that is from, you know, people who like insulate their homes. It's called the R value. So I'm just going to maybe erase something here just to kind of show you a different way of solving this. So let me just take all that out. Okay? Just so I have some more space. And just kind of point out that we know that Q over delta T is Ka delta T all over L. But you could rewrite it as essentially A delta T and then L over K. And so if you have many layers, you could write it as Q over delta T equals A over delta T and then L1 over K1 and L2 over K2 and continuing on. So this by the way, this L over K is what we call the R value. So when you sum, for example, all the Li over Ki, so all the length of it, the thickness of the layer, divided by its thermal conductivity, this gives you what we call the total R value for your layer. So let's say you have a home that's made up of like brick and then insulation and then, I don't know, wood inside or something, so wood paneling. Then you can find out what's called the total R value. Okay, not part of the AP exam, but just kind of interesting to know. So another quick way to solve this problem is to just say, if you were to find the total heat flow rate, you could just say area over change in temperature, and that's the change in temperature of the entire composite of materials, and then do L steel over K steel, and then L copper, all over K copper. So then you just plug in 0.0004 meters squared. Change in temperature is really just 100 Celsius minus 0 Celsius. And then you put your thermal conductivities. So the thickness of the first layer is 10 centimeters, right? 10 centimeters. And then it had a thermal conductivity of 14. So 10 centimeters all over 14 joules per, actually that's centimeters. Probably I should convert that to meters, by the way. 0.1 meters, and then this is in joules per meter, degrees Celsius, and is there anything else? Seconds, yes, seconds. Then the next layer is 0.2 meters, and its thermal conductivity is 390, right up there. 390 joules, meters, degrees Celsius, seconds. And then when you plug that all into your calculator, you get the same answer as what we had before. You get 5.22 joules per second. So if you're trying to find the total heat flow without knowing the intermediate temperature between the two surfaces, you could use this kind of shortcut method, right? If you're asked to find the temperature in between, then you're going to need to do the other method that we did earlier. I suppose you could find the total heat flow rate, by the way, this way, and then you could just then use this formula here just for steel, and then just solve for the change in temperature. So that's another way of doing it. But anyway, now you have different ways to look at it. Okay, I do believe, by the way, my answer down here is wrong. It's supposed to be 5.22 watts. Okay, that's it for this rather long example.